we'd like to combine some of the elements we've seen on escape rates on the one hand and mixing on the other hand. So our setting will have a graph G. So it will be connected and undirected, and it will be a simple graph, meaning no multiple edges and no self-loops. We will consider the Markov chain will be simple random walk or lazy simple random walk. Both of them will work on G. And the goal is to compare mixing time to the diameter. So for any graph, we have a natural graph metric. The distance between two nodes is the length of the shortest path between them. The diameter of the graph is just the maximal distance between two nodes. And we want to see how that relates to the mixing time. So so in general, without conditions, you cannot bound the mixing time from if above. So the diameter will denote by capital D above using D. Because if you have a graph like a graph the type we mentioned, so here is a complete graph. This is a complete graph on n over 2 nodes. So all the edges are present. And here is another copy of the complete graph on n over 2 nodes. And we connect two of these nodes by a single edge. Then the mixing time here will be very large, in fact, order n squared. So yet the diameter of this graph is just 3. Right? You can get from any node to any other node. So so to see that, at least intuitively, why the mixing time here is n squared, let me explain. So if suppose I start with some node here, and let's take epsilon equals a quarter, so we want to understand T mix, which is T mix of a quarter. So if I start here, then I can look at this target set A. So it has measure 1/2, so it's the set on the right. And I can ask how long until PTXA, right, to get to this mixing time, we need PTXA to be close to 1/2. So we need to have a substantial chance to reach this side. Now, so the first question is, how long does it take to reach this side? So to reach this side, the only chance I have is via this vertex, this connecting vertex. And this vertex I visit with, each time I go to it, with probability about 1 over n, 1 over n over 2 minus 1, but order 1 over n. So starting from x, it will take me about n steps, or about n over 2, till I first visit here. But each time I visit here, I'm not guaranteed to cross. Quite the contrary. Each time I'm here, the particle sees only one edge going right, and it sees n over 2 edges going left. So the chance, even when it is here, the chance it will make the crossing is only 1 over n, or 2 over n. So you have to wait for a rare event with probability 2 over n, but even that is only not guarantee of success. You need for a doubly rare event to happen, which has probability constant over n squared, or 4 over n squared. Namely, you need to visit this vertex and then take this step. So it's easy to see by comparison to a geometric variable that this will take order n squared. So if I wait for a time which is a small constant times n squared, n squared over 10, then the chance is rather small, n squared over 100. If we don't care about the constants here, then the chance is rather small that in this time I will have crossed to a. So pt xa minus pi of a will be, in absolute value, larger than a quarter. So the mixing time here is at least n squared. On the other hand, it's easy to see that the mixing time really is of order n squared. So we write comparable to n squared. And this we can see, for instance, using the coupling method. So we start with two particles, and the worst case is when they are both on different sides. And they start walking, and the same argument as before says that by time n squared, one of them is likely to cross to the other side. It's very small probability that they will both cross. So first one will cross, and it's small probability they will cross at the same time. So when the first time one of them crosses, say x first reaches here, after they are in the same side, they will couple. We can couple them very quickly. If we run them independently, they will couple in n more steps, but in fact, we're allowed to choose any coupling, so we can, in fact, couple them in essentially one more step once they're on the same side. So, but getting to the same side, that really takes order n squared. So the mixing time here is n squared. So there is no upper bound. However, we will see for Cayley graphs, a T mix is going to be bounded by a constant times the degree times d squared, okay, times log n. So what is a Cayley graph? Cayley graph is obtained from a group. So we have a group which is finitely generated by some set of generators S, and what we do is the vertices, we take x and y in the group, and they are connected if x is in y times S. And S is a set of generators of the group. So, so here I'm assuming people have some background in group theory, but let me say that what's important for us in the Cayley graph structure is it's what's called transitivity. A Cayley graph has the property that all vertices look the same, which formally means for any two vertices of the Cayley graph, there is a graph homomorphism that takes one vertex to the other one. So Cayley graphs, there are a lot of them because there are a lot of finite groups. So classical examples are permutation groups and various subgroups of permutations, but go to your favorite algebraist and he will tell you about many other interesting groups. The ones that are simplest to visualize are the lattices, the tori, and there are of course many infinite groups as well, free groups. I will maybe mention one other interesting example later, which is called the Lamplighter group. But for now, I want to say, I just mentioned this. We'll come back to this point. But this is about upper bound. So, if usually we're interested in graphs where the degree is small or logarithmic. And here, so we have a degree factor, a log n factor, and the main term here is this diameter squared. So this is often a good bound, but not always. So if we look at the case of the cycle that we looked at before, then there this bound is reasonable. We know the truth there is the mixing time is n squared, and this will give and n squared log n. In fact, this bound is based on the bound for the relaxation time. The relaxation time is at most 2 times d squared times the degree. And then once you know that, you easily get the bound for the mixing time because of the relation we discussed between the mixing and the relaxation time. For this to hold without further conditions, you really need to consider the lazy simple random walk, because some groups, for some groups, the Cayley graphs are bipartite, so the random walk itself will not mix. You need to consider the lazy simple random walk. Okay, so we'll come back to this point, but now I want to talk a little about lower bounds for the mixing time using diameter. So there is one trivial lower bound, which says that the mixing, let's say for epsilon, which is less than a half, the mixing time is at least the diameter over 2. And this is because if this is our graph, here are 2 points x and z that are diametrically opposite, so their distance is exactly d, then if we look at any time which is less than half the diameter, then when I start from x, I can only reach the points that are closer to x. When I start from z, I can only reach the points that are closer to z. So if I define this set A, say, which are the points y, so that the distance, maybe I want to call the distance now rho. So rho will be the graph distance. So if I look at the set A, which are points y, so that the distance from y to x is at least d over 2. So this is the set A here. So these are points distance at least d over 2. Then PTXA is going to be 0 for t which is less than d over 2. But if I look here at the set A complement, I have to continue. Do people see what's down there, or is it hidden? So again, let me redraw this picture. This is x, this is z. We're going to reuse this picture for a less trivial bound in a moment. So this was the set A. A was the points y, so that the distance from y to x was at least d over 2. Then, PTXA was 0 for t which is less than d over 2. You cannot get there. On the other hand, if you look at A complement over here, the complement is contained in the set of y's, so that the distance from y to z is bigger than d over 2. Right? Because the complement is exactly the set of y's, so that the distance from y to x is less than d over 2. And if a point had distance to x less than d over 2 and distance to z less than d over 2, we would get a contradiction from triangle inequality. So we have this containment. And so since A complement is contained in this, same reason gives PT of Z A complement is also 0. So if we look at the quantity d bar of t I defined last time, so what was d bar of t? It's the maximum over all choices of xz of this quantity pt xa. It's the maximum over all choices of x and z of the total variation distance. So it's bigger than pt xa minus pt za in absolute value. But this is 0 and this is 1. So
Yuval, do remind us what was d bar of t?
Yes, so d bar of t was defined as the maximum over all pairs xz of starting points of the total variation distance of the distribution at time t starting from x and the distribution at time t starting from z. And the total variation distance itself is the maximum over sets A of this. So the total variation distance is just the maximum over all choices of x, z, and a of the right-hand side here. But this is 1. So in fact, so we get that for this t, d bar of t is 1. And then that implies, remember that d bar of t was bigger than d of t, but was smaller than twice d of t, just from triangle inequality. So just using that right-hand inequality, you get that d bar of t is at least a half. Okay, so this is the d of t is at least a half. So the mixing time the mixing time is at least the diameter over 2. So that's the trivial bound. But it turns out we can use essentially the same picture together with the Varopoulos-Karn bound to get something better. Now, I said this is a trivial bound. There are cases where this trivial bound is attained. One example are these so-called expander graphs. So expander graphs are graphs of bounded degree where the relaxation time is order 1. In other words, there is a spectral gap. So these are, I won't have time to construct them for you, but expander graphs, or just expanders, so these are, it's really more precise to talk about an expander sequence. So these are graphs Gn where the degrees are bounded. The size, say Gn has size n, so the size goes to infinity, and the spectral gap is bounded below. Or in other words, the relaxation time of, say, the lazy simple random walk should be bounded above. So it's not an obvious fact that expander graph sequences exist. Again, so with this definition, I'm saying that something is bounded. So for a fixed graph, everything is bounded. So really, you should talk about an expander graph sequence. What? I didn't. Okay, so I emphasize. Okay. Maybe I switched. Upper bounds need the Cayley graph. And I'm delaying the upper bounds to later. They're more sophisticated. Lower bounds don't need any Cayley graph assumption. Okay? So sorry I was shifting, but I wanted to give you a preview. We'll prove later. And I gave an example showing that there is no upper bound, no reasonable upper bound on the mixing time using the diameter, because the diameter could be 3 and the mixing time can be huge and squared. For Cayley graphs, there will be a good upper bound, but I'm delaying that to later. And then I'm shifting gears and talking about lower bounds. So there is an easy lower bound of diameter over 2, which I explained. And this easy trivial lower bound is sometimes sharp. And an example where it's sharp are these expander graphs. So these are graphs of bounded degree. You can take them to have degree 3. And yet they have a spectral gap bounded below or relaxation time bounded above. So the first example of expander graphs was actually constructed by Pinsker in Russia around the early 70s. And the construction was you take n over 2 vertices here, n over 2 vertices here, and combine 3 random permutations. So you take a permutation from the left side to the right side, okay, and you just take 3 random permutations, or you could take 2 random permutations and 1 just the identity. That's good enough. So by combining this, you get a 3 regular graph. Every vertex has 3 neighbors on the other side. Since we combine 3 permutations, there's some chance this will create multiple edges, but with a substantial probability, probability bounded away from 0, there will be no multiple edges here. So with a substantial probability you can calculate, this will give you a legitimate simple graph with certainly there are no loops, no self loops, And with substantial probability, there are no multiple edges. So with some constant probability, that goes to a constant. So if you look at this event, you get a random graph. And what Pinsker showed is that with high probability, this graph will be an expander. So although at the time, the different notions of he didn't use the spectral gap definition. He used the expansion definition. So there is an equivalent definition of expansion, more combinatorial. It took until the 80s to get deterministic constructions of expanders, and the most famous is the Lubovsky-Philip-Sarnak Ramanujan graphs. I will show you some pictures of those in the last lecture tomorrow. But these graphs have relaxation time order 1, so that means the mixing time is order log n by the kind of bounds we discussed yesterday. And they also have a diameter, which is log n. Certainly, any graph of bounded degree cannot have a diameter which is smaller than order log n. And so these graphs have diameter and mixing time both order log n. So it shows that this bound can be sharp up to constant. But in many cases, it is not satisfactory. So let's see a better bound. So better bound, T mix is bigger than diameter squared over constant. I'll put 16, but this constant is not optimal. T mix is bigger than diameter squared over constant log n. So if you're ignoring logarithmic factor, it tells you that diameter squared is a lower bound, okay, and then there is this log n correction. So again, the same example of expander graphs, for expander graphs, this bound is the same as before, but for most graphs, the diameter is bigger than log n, and then this bound is better than before. And again, log n is the minimal possible diameter if we're talking about graphs of bounded degree. So usually this bound is better than the previous one. So let's prove it. So we're going to conveniently use the same picture I have on the right board, the same set A and A complement, but we were just going to give a better estimate for PTXA. So remember the Varopoulos-Karn bound. So it says PTXY is less than root pi. So, okay, so this is the more general bound than what I proved, but I assume you've all used the time to look in the lecture notes or in the book that has the general proof. 1 second. So we have e to the minus a factor of 2, e to the minus rho squared of xy over 2t. So that's the Varopoulos-Karn bound we're going to use. Krishna, you had a comment?
Yeah, the T mix is for a fixed epsilon.
Yes.
So if you were to make the epsilon depend on n, then you will get big trouble, right?
So that's right. So then it's a different game, but usually we fix epsilon. Yes.
For each fixed epsilon, it's a lower bound.
So yeah. So I didn't. So when I write T mix and I don't write what is epsilon, I mean epsilon is a quarter. This was a convention, but if you want to be more, let's be more precise. So this is true. Okay, this is true for epsilon strictly less than a half, provided n is large enough. Okay, so for any epsilon less than a half, this is true if n is large enough, bigger than some n sub epsilon. Okay, so this is more precise. Okay, so we're going to use this bound. So if the graph is regular, if all the degrees are the same, then this factor is 1. Otherwise, this factor is at most root n, because the largest, since we have a simple graph, all the degrees are at least, and it's connected, all the degrees are at least 1 and at most n. So I can write in our graph case, this is at most 2 root n e to the minus rho squared xy over 2t. So I'm going to use the same, I won't repeat. So I want to use the same sets A and A complement defined here. So this is A complement is contained in that set. So we're going to look at our graph as before, fix two nodes x and z that have their distance maximal, rho xz equals d. We have some points, such point d. We define the set A as before, and now we want to get a better bound for ptxa. So we're just going to sum over the elements of A. I don't know what is the size of A, but it's certainly at most n. So let's put, so we can put here 2 n 3/2 e to the minus. Now this factor in all points, so I want to write d squared over 8t. Because this, because rho of xy is at least d over 2 for y in A. That's the definition of A. Right? So this is what we have. Yes. N to the power n to the 3 over 2, because we have root n here and n from the size of A. So ptxa, we are summing over all elements of A, this bound up here. Okay? Anything else not clear? I jumped a step, but I hope it's okay. Summing over the elements of A. So now, so the idea of the choice of t, so here is, so if we take for t which is less than d squared over 16 log n, we get that ptxa. So we're going to just plug in this value of t. The d squared cancels, and we get, well, let me write it, 2n to the 3/2 e to the minus 2 log n. In other words, we get 2 over root n. Okay? Please stop me if something is unclear. Okay, now the same argument gives that if I look at pt of z and A complement, again, all the points in A complement have distance at least d over 2 from z. So exactly the same considerations tell us that this is also less than 2 over root n. So now if we look at d bar of t, it's bigger than pt of za minus pt of xa. But pt of za is at least 1 minus 2 over root n. So we get that this is bigger than 1 minus 4 over root n. Because from this inequality, we have that pt of za must be at least 1 minus 2 over root n. Okay, so we have this. So d of t is bigger than a half minus 2 over root n. Okay, so if n is large enough, this is going to be bigger than epsilon, because we assumed epsilon is less than a half. Okay, so that proves this inequality. Okay? And if epsilon is like a quarter, then the n that you need is not very large, right? You just need 2 over root n to be less than a quarter. Any questions about this? So as simple as this proof is from Veropoulos-Karn, it's it's not something that's really obtainable by other means. So the bound of it's a pretty good bound. There are many examples where diameter squared is the right order of mixing, though it's not always. And this gives you the diameter squared with this log correction. So it again shows the power of the Veropoulos-Karn inequality. Yes?
I'm going to take you back to the first step. How
Yes.
do you argue that pi y by pi x is less than or equal to n?
Okay, so I said that what I'm considering is not a general Markov chain. It's now simple random walk or lazy simple random walk on a graph. So we have to recognize what is this stationary distribution for such a walk. And that is just the degrees. So if you look at the vector of degrees, then you can check immediately the reversibility condition. So pi y pxy equal is just, if you take pi, which is a degree, then you get pi y pxy is just 1. So it's true. So you get reversibility. So the vector of the degrees is a reversible and hence stationary measure for the Markov chain, which is simple random walk, and it also applies to lazy simple random walk. Okay? So then what we're using is the ratio of degrees is at most n because we have a simple graph. We don't allow multiple edges. Okay? Any other questions? All right. So I'm going to move on to upper bounds. So I want to state a theorem about transitive graphs. I'll only prove it in the case of Cayley graphs. So this is, on the one hand, it's a theorem that appeared in Annals of Probability just a couple of years ago, but I can present the main idea here, and it's a theorem about the rate of escape in a Cayley graph. So if G, or a transitive graph, if G is a, so maybe let G be a finite or infinite a Cayley or more generally, transitive graph. Okay, and what I want to look at is the rate of escape. So let's write the degree equals d. So these graphs are automatically regular. The degree of every vertex is the same. If it's a Cayley graph, the degree is the size of the set of generators we're using. And we need to look at the expected distance, okay, from x0 to xt. So xt will be the simple random walk. T is the time parameter. We need to look at the expected distance squared. And we want to say that something about this. So expected distance squared is at least, okay, T over D, if G is infinite. If G is finite, I need a condition T is at most TRL. Okay, so this is a case where the statement for infinite graphs is much cleaner than for finite, but in this case, the proof for finite graphs is a little simpler. So I will focus on the proof for finite. But the statement in infinite graphs is now one. So okay. So let's look at infinite Cayley graphs. Of course, the most familiar are Z and ZD. And there we know that the expected distance squared grows linearly in time. It's natural to guess that these are the slowest groups, and this theorem says this is essentially true. But when we think of how to prove that, natural approach is to say, well, if I'm in Z or in ZD, it's always true that wherever I am, at least half my neighbors are further from the starting point than my current locations. So I can just couple my walk to a walk on Z and say that the distance is always growing. This is true in ZD, but it definitely is false in general Cayley graphs. So there is kind of an amazing fact of group theory, which says there are Cayley graphs with dead ends. So what is a dead end? So we have this Cayley graph. A dead end is a vertex where all its neighbors are closer to the identity than the vertex itself. So there is no way to go further. Every step, everywhere you go, gets you closer to the identity. So it's kind of shocking that these dead ends exist. And in fact, they exist in a bad way. There are some vertices where every neighbor is closer to the identity. And moreover, if you want to get further from the identity, you have to go quite a distance closer before you can have a chance to go further. So they really have these deep dead ends, deep cul-de-sacs. And to think that this is possible in a transitive graph is very surprising. I'll show you some examples later. But this means that this coupling approach to prove lower bounds for distance is really doomed. And another approach is to use what's called heat kernel or transition probability bounds. So we can say, well, one reason the walk has to escape is if we can say the probability of any specific point is small, so it has to, the walk cannot stay confined in a small ball. And that approach can work, but it only gives a lower bound of t to the 1/3 on the expected distance, or t to the 2/3 on the distance squared. So this is quite a sophisticated approach, again, due to Veropoulos and continued by many others. But it doesn't give a sharp bound. So for a long time, people like me who spend most of their time thinking about random walks were puzzled because we know all the examples we knew and all the examples all our friends, the algebraists, could produce had lower bound of root t, but the proofs that were based on heat kernel bounds and isoperimetric profiles only gave this t to the 1/3. So how to get such a bound? The idea came from a French mathematician, Anna Oeschler, who suggested to use a method called the mock embedding theorem. So I'm not going to tell you the details of that, because in the end we found an elementary approach. But the mock embedding theorem says that amenable groups can be embedded into Hilbert space by an equivariant Lipschitz map. And so the rough idea is to take the random walk, map it by some miraculous harmonic equivariant mapping into Hilbert space. This harmonic map will take the Cayley graph, will map it into Hilbert space in such a way that the random walk will map to a martingale in this Hilbert space. And then for martingales, we can easily compute L2 norms using orthogonality of increments and get the result. So it was really kind of an amazing approach, especially as the mock embedding theorem was considered quite deep. But so after we got this hint from Anna Oeschler, James Lee, who is a computer scientist but also a probabilist at the University of Washington, and I were very puzzled. We thought, well, there should be some more direct explanation, and we found one, but it's not really independent of Anna's ideas. It's inspired by Anna's suggestions. So let me tell you how this goes. So in the infinite case, there is a technicality, which is that you also need either G amenable or T large. I'm not going to focus on the infinite case so much, but okay. So the key lemma we will use is based on a method of spectral embedding, which is extremely useful now both in probability and in computer science, in clustering problems and so on. So the idea is, instead of using some mapping into a infinite dimensional Hilbert space, we're going to map into Euclidean space using some eigenfunctions of the chain. That's what's going to come. So, but first, what is the statement? We're going to take, given a function f in L, it's going to be a function in L2 of G. So G is our graph or our group. We're going to identify the graph and the group. Now, L2 of G, well, if G is infinite, it means, well, functions from the group to R, which are square summable. If G is finite, it just means all functions from G to R. They're all in L2 of G. We're going to define the Dirichlet form. So maybe I'll call it ET. So this is the energy form, the Dirichlet energy at time t of f. And it's okay. So this has two equivalent definitions. So it's so P is our transition matrix. I minus PF multiplied by F. I should stop soon, right? What? 1020. Okay. So ET of F is this. What? P to the T. Thank you. Expectation of the distance squared from x0 to xt is at least 1 over d, so d was the degree, times Et of f over E1 of f. So, okay, so I'm assuming here that f is not constant because for constant f, E1 is going to be 0. But so let's see first. So again, I hope it's clear what I'm doing here. This is, I'm taking p to the t applying, and I minus p to the t applying to f, and taking inner product with f. This is just inner product in L2 of g. So this is just, there's no pi here. The measure is just counting measure. So this is just a sum. So first, let's see, let's deduce the theorem in the finite case. So note that this theorem, this lemma can be applied to any function f. And the proof of this lemma will be based on the spectral embedding. What's easiest for me to show now before the break is how we can use this lemma. So in the finite case, let's apply this lemma with f, which is an eigenfunction. So take pf equals lambda f. And we're going to take lambda to be the second eigenvalue, or the largest eigenvalue in absolute value. And just apply it for this f. We can take f to be normalized in L2 of g. Okay, so that doesn't matter. In this case, what is Et of f? So you see the formula here. Now, it's just 1 minus lambda to the t, ff. So it's just 1 minus lambda to the t. Which we can factor. So the lemma tells us that the expected this rho squared of x0 xt is at least this sum but now we are assuming t is at most t rel, which is 1 over 1 minus lambda. So that means that lambda is bigger than 1 minus 1 over t. Right? So if you just, right, so this is bigger than 1 over d times the sum 1 minus 1 over t to the j equals 0 to t minus 1. And now you can do this efficiently or less efficiently. Let's do it generously. So 1 minus 1 over t to the j is bigger than 1 minus j over t. And this is a sum that we can do. We get t from this, and at most t over 2 from this. So this is bigger than t over 2d. If you're a little more careful, then this constant of a half you can improve a little bit. Some like 1 minus 1 over e, but we don't care about that too much. So that proves this statement given the lemma. But so we'll continue with the lemma after the break. Yes, or you can think of the lazy walk where lambda is bigger than 0, or take the absolute values. Yes. If now one thing to notice, if lambda is not so, in most cases the relaxation time has to tend to infinity. So 1 minus lambda will. So the lambda will tend to, lambda 2 will be very close to 1. So you really don't, so this argument, what matters is really lambda 2, not the biggest lambda in absolute value, but really lambda 2. The one that's closest to 1 is what matters. And so really that's what one should consider here, and not the one. Even if the graph is bipartite, so it means there's an eigenvalue of -1. What we would need to consider is the second largest eigenvalue, not in absolute value, but really just the one that's closest to 1. Okay, so we'll continue after the break.